We talk a lot about how climate change is affecting water availability, access, quantity, quality, and so on and so forth. And there are many places which are relying on desalination, Israel, Middle East as a whole. It takes money, and of course, if it's a big country with a coast where you do desalination, then how to pipe it in and how much it will cost, and what to do with all the brine you release when you convert ocean water into fresh water. Theoretically, it's considering just how big the oceans are, how much of the earth is oceans. We shouldn't have water problems if we could just desalinate and get it to everybody, right? So this is a related issue. High levels of sodium drinking water have been linked to increased rates of pre-eclampsia in Bangladesh, a disease. I should make sure I say it correctly. Preeclampsia is something, I looked it up when I read it, but this was only a few days ago. So I will do it live here when I'm recording, which is not the best way to do these things. But preeclampsia is a potentially dangerous pregnancy complication characterized by high blood pressure. Usually begins after 20 weeks of pregnancy. In women whose blood pressure has been normal, can lead to serious and even fatal complications. Okay, so that high level of sodium comes from excessive irrigation or extracting groundwater and intrusion of ocean water and so on. Unconventional, so this is a title of the kind of a news article, is Chemistry's Salinity Headache, Unconventional Methods for Desalination Could Create More Drinking Water, Help Many Industries to Deal with Problematic Brines, and increase lithium supplies for batteries. There is a way to use filter salt water and extract lithium, or ocean water and extract lithium. So here is the conventional way people have been thinking about. The MIT team's invention builds upon electrodialysis, a method that uses an electric field to remove salt ions from water. The system consists of water pumps, you can see here, an ion exchange membrane, you can see plus minus is here, and a solar panel for energy. So you are using renewable energy in that sense. There are advantages for this. They are producing significant amounts of water in demonstrations, and if doesn't need conventional fossil energy, they are trying to do it using solar panels. And I've talked about another method of doing it just near the coast, where again you can use renewable energy to do that and produce fresh water. So let's read off some of the text. People have been separating salt from water for millennia, harvesting both salt and fresh drinking water from salty seawater, but there are limits to what can be done, sometimes with drastic consequences. And people in an ancient Mesopotamia couldn't work out, I added an and for no reason, when people in ancient Mesopotamia couldn't work out how to desalinate their irrigation water and prevent salts from accumulating in their soils, their society collapsed. It's kind of the world's oldest, most boring but serious problem, says Sujay Kaushal, a hydrologist at the University of Maryland in College Park. Sujay is a colleague. In fact, when he was hired, I was the chairman of the search committee. This problem is now growing more pressing as salinity levels creep up in fresh waters for a slew of reasons. Rising sea level are pushing salt into coastal groundwaters, which is what I mentioned here in the case of Bangladesh, while excessive groundwater extraction in other places is drawing deeper, saltier waters up into the aquifers. And human activities, from de-icing roads to washing clothes and fertilizing fields, are polluting surface waters with many kinds of salts as well. Last October, Kushal and his colleagues reported that salt levels in major streams and rivers around the world are booming. Some bodies of water are now several times saltier than they were a few decades ago. Freshwater Desalination is a massive problem, not just a regional one, says Sujay Kaushal. He reports a lot of this in the media every year. A second related issue is the growing burden of problematic waste brines. A variety of industries, from oil and gas extraction to the desalination plants themselves that produce drinking water, create salty wastewaters that are costly to dispose of. We need to do something with the brine, says Menachem Elimelech, an environmental engineer at Yale University in New Haven, Connecticut. On the flip side of these problems is the salt mining industry itself. Hundreds of millions of tons of mineral salts are extracted every year from the rock or briny waters. Dead Sea is a major source of potassium. Great Salt Lake in Utah breeds magnesium. Mining companies seeking supplies of lithium, a metal crucial for batteries and green technologies, are turning to brines around the world. Researchers who sense opportunities in these fields are hoping that they can extract salts from waste brines, turning the problem into profit while squeezing out some more fresh water of the brine. To do all that, scientists are now exploring techniques to separate salt from water more efficiently using electricity, new materials, and solvents. With a wide range of brine chemistries to tackle and a host of different goals, there isn't one killer technology, says Shi-Hong Lin, an environmental engineer at Vanderbilt University in Nashville, Tennessee. This is like 1,000 different problems, says Lin. So here is lithium mine in Chile. It's spreading brines over vast areas to evaporate water. So lithium and brine production are intimately linked. So if you can do this by taking care of the brine problem, you can actually solve it. So I will actually add a little more information on lithium mining from another paper. I will pause this after this is finished and then add another slide. Super salty. So it's clear that extremely salty water isn't healthy for humans, animals, or plants. Our bodies have evolved to maintain certain internal levels of salt in the waters in the body and cells, and if we go into the water, salt water too much, osmosis begins to affect us, and of course we cannot drink salt water, so otherwise it would be great, right? Drinking seawater, which contains about 3.5% salt, most of it sodium chloride, can shut down our kidneys and be fatal. Brackish groundwater, which contains around 0.1 to 1% salt, is typically desalinated before drinking, but the health impacts from less salty waters are murky. It's not clear that it's safe, but it's not unclear how unhealthy it is. Whether you can drink it for 30 years without any problem, not increasing any risk of disease, nobody knows, says Lin. The trouble is that reverse osmosis has a limit. So I'm jumping ahead. It discusses the methods, typically evaporating, either using solar power or something else, or there are other methods, but reverse osmosis also is used typically to provide you clean water, and then sometimes it removes all the minerals which are also useful, so they add some minerals back and so on. So if you read bottles of water that you buy, often it says reverse osmosis, UV treated, and so on. But that reverse osmosis has a limit. As fresh water is extracted, the source of waters get ever saltier, making it harder and harder to continue the separation process. This is an inescapable problem, says Christopher Follows, a chemist at the Saline Water Conversion Corporation, SWCC, in Jubail, Saudi Arabia. All forms of desalination leave a waste brine that needs to be managed. Right? I think you know what osmosis and reverse osmosis are. Osmosis is a semi-permeable membrane which allows the higher concentration of solvent to go from one side to the other, so you can separate the dissolved materials from the solids from the solvent. Right? Mine the brine. So reverse osmosis is where you reverse the process and to get water. Mine the brine. Some waste brines are simply put into the ocean. In California, a pipe system called the brine line carries waste brines that are produced more than 100 kilometers inland out to sea. In other places, the most economical solution is to inject waste brines underground in a spot far enough away from utilized groundwater. Okay. This technique has been criticized for its potential to cause micro earthquakes. So we do injection of water to extract a little bit of oil, shale, etc. called fracking, which also causes micro earthquakes. So this also does the same thing. Whenever you inject things into little cracks and nooks and crannies, you can cause many earthquakes, right? Fresh Solutions in Saudi Arabia, recognizing the opportunity to bring an extra revenue while producing more fresh water, the government-owned SWCC is now building a demonstration plant to harvest sodium chloride among other salts from seawater desalination wastes. The plant, scheduled to break ground at the end of this year in Haql, Saudi Arabia, uses an emerging salt sorting technique called nanofiltration as part of a long string of processes, says Fellows. Like reverse osmosis, nanofiltration works by pushing water molecules across a membrane, but the membrane has larger pores than that also allow some salt ions through. Dissolved salt ions carrying only one electrical charge, such as sodium, potassium, and chloride, can cross the barrier, whereas those with two or more charges, such as magnesium and calcium, stay behind. The SWCC's key challenge is to produce sodium chloride that is pure enough for the chlor-alkali market. To avoid both evaporation and the use of membranes, Gibbs team at Columbia University are instead looking into chemical solvents. So there is a video associated with this that you can go and see. One promising candidate is an off-the-shelf solvent called diisopropylamine 5. The solvent floats on top of salty brine and at low temperatures selectively sucks water molecules into itself, leaving most of the salt ions behind. At higher temperatures, the diisopropylamine switches to repelling water and spontaneously expels the water that it has absorbed, so the water can be recovered and solvent reused. So it's a solvent like a sponge, absorbs water and then can be released under higher temperature. Yet more inspiration could be found in nature. Highly selective channel proteins embedded in cell membranes. That's one example. One type of ion channel allows just one sodium ion to pass through for every 1,000 potassium ions, says Elimelech. His team is currently working on membranes that mimic these channel proteins, although for now they are in the earliest stages of development. So the MIT solution we saw is essentially doing the same thing. It is a electrodialysis method that uses electric field to remove salt ions from water. It's not as selective as the one we are discussing here from Gibbs group from Columbia. Okay, so finally the price barrier, of course, when you do all these fancy things, whether any of these ideas will take hold depends on economics. If the SWCC mined all the available sodium chloride from Saudi Arabia's seawater desalination brines, Fellows notes it would be enough to supply 1/3 of the world's market. So there is a lot of salt being potentially produced if they do it this way. Meanwhile, waste brines left over from brackish water desalination would offer the plentiful mineral gypsum, but it's unlikely that unconventional brine mining could compete economically with conventional quarrying from rocks directly. So when we looked at technologies for sustainably harvesting the ocean, we talked about many minerals that are in the ocean water with various concentrations and how expensive they are to extract, and this is another example, gypsum. New markets such as the advent of salt-fueled technologies including zinc bromine batteries could create fresh demand for certain salts, says Fellows. Regulations could also play a part, either by making it more expensive to dispose of waste brines or by incentivizing the use of brine-sourced salts in various applications. for instance, brine sourced gypsum in road salts. One thing is clear, freshwater needs are increasing. Addressing the current limits of desalination with new technologies is important, researchers say. But it isn't an alternative to the still essential step of conserving freshwater. It will always take energy, time, or land space to separate salt from water, so there will always be a price to pay for desalination. There is no magic there, says Elimelech. So I will pause here and bring you a slide on sustainable mining of lithium, which is related to this brine issue. Okay, give me a second. Okay, so it took me a while to do this, but you won't see the difference. It pauses and then jumps back in when I restart the recording. So by the way, the previous article I just was reading is from Nature from July 2024. Here we are with another article from this review here that is fairly long, so I'm just going to take a few major points. This talks about environmental impact of direct lithium extraction from brine. So this is how it's related to what we've been reading about desalination and the problem of getting headache of getting rid of the brine. The key points here: freshwater consumption of direct lithium extraction needs to be urgently quantified. Many direct lithium extraction DLE technologies might require larger freshwater volumes than current evaporative practices, compromising their applicability in arid locations. Chemical processing is not completed until a pure solid product is obtained. Energy consumption of DLE should be estimated for the overall process, including potential water extraction or evaporation from pure but dilute lithium chlorine solutions, as is the case with many DLE technologies. Lithium ion LiCl is lithium chloride, I guess. Lithium ions are only a minor component in continental geothermal and oil field brines, but thus, from a circular economy perspective, there is potential for extraction of more than one valuable mineral, notably borates, magnesium, potassium, and sodium salts, which we also mentioned in the previous section of this podcast. Knowledge of this precise number, distribution, and depths of brine and freshwater wells is vital for hydrogeologically modeling lithium brine deposits. The distinct hydrogeology of each salar means that each deposit should be modeled independently and results from one exploitation cannot be directly extrapolated to another. Environmental monitoring should be permanent and precede the start of the exploration, as environmental impacts might only be observable in the long run. Water monitoring requires gathering precipitation data, river flows, and sufficient number of observations wells to follow water tables at different locations. So emphasis here is on environmental impact of direct lithium extraction from brines, but I'm just trying to relate it to the overall brine problem we just discussed. Environmental monitoring guidelines have been drafted from evaporating technology in mind, but they should also be applied to the implementation of any DLE technology which still consumes brine, uses fresh water, and produces residues, the latter two hopefully at considerably lower volume. So here are the locations where the brine extraction or direct lithium extraction is happening. Let me just add a formal information to the so a salar, SALAR, is a brine. When you create these pits, so a salar is a depression in the earth that is covered in salt and may or may not be basin of an evaporated lake. The Spanish word salar means salt flat. Okay, so let's leave it there. Just I wanted to make sure that I made it formally clear. So here is Clayton Valley, 6,000 tons per year of LCE. Geothermal deposits, Zabayu, Dongtai, and Shitai salt lakes, 37,300 tons per year LCE. And here are some other numbers from Atacama Desert and so on. So these are lithium sources and exploitation, active lithium mining from brine facilities and corresponding production capacities in 2022 for the following salars: salt pits, salt flats, Clayton Valley, USA, Lake Zabayu or Zabuye, Dongtai Salt Lake and Shital Salt Lake in China, Salar de Atacama 1 and 2 in Chile, and Salar del Hombre Muerto and Salar de Olaros in Argentina. The inset zooms in on the lithium triangle in South America, which has the largest identified deposits in continental brines worldwide. Deposits that are mentioned in the review but are not currently exploited are also shown here. Salar de Uni, so I won't go into those details. So you can see here solar evaporation, so waste is produced, reagents, lithium carbonate extracted and transported out, freshwater aquifer is being used to extract water for this processing, and increasing LiCl concentration here in the brine. And then here is the saline aquifer from where you are extracting the brine into the pond for solar evaporation. So this is the schematic representation of evaporatic technology. The first step is brine pumping from underground reservoirs. Brines are poured into large shallow open air ponds where 90% of the original water content is lost via evaporation accelerated by solar radiation and wind. LiCl concentration increases gradually and salts from other cations crystallize in the ponds as saturation is reached. Concentrated brines then enter a refining plant for crystallization of the final product, usually lithium carbonate. Freshwater and chemicals are used at several steps of processing. So it's a slightly different but related problem in terms of the brine problem. And let's just also make sure, I kept saying LiCl, but let's see what that is. That is the chemical name. Of course, it is lithium chloride. It is an ionic compound that is made up of positively charged lithium ion and negatively charged chloride ion. Okay, so hopefully it's useful. Yeah, let me leave it there.